This is a flux question, I should say. So let's look at the question. It says you are told that the net electric flux through the surface of a sphere which has a radius of 0.1 meter, area of 0.13 meter square, volume of this is minus 26 Newton meter square per coulomb. You can use this information to 1. Find the net charge inside the sphere, 2. Find the magnitude and direction of the net electric field at point P somewhere on the surface of the sphere. Choose all of the above statements that are true. A is 1 only, 2 only is B, C is both 1 and 2, D is neither, and E is none of the above. You have 1 minute, talk to a person next to you.
Yeah, I would say both.
Okay, notice you can only use the information that you have been given. You cannot conclude something else. Whatever is given is what you have. All right, the correct answer here is actually 1, A, that is A. So, the correct answer is A, and can anybody who got the correct answer explain why they chose that? Please go ahead.
Because you can't determine where the direction would be. You only know, you can't determine like how the charge is distributed.
Exactly. All you know, if I gave you a closed surface here, right? This is my sphere. All I can say, Gauss's law says this. Gauss's law says that the flux should be equal to Q enclosed divided by epsilon 0, right? So using Gauss's law, I can say Q enclosed is equal to phi, which is the flux, times epsilon 0. So I know that Q enclosed must be equal to whatever is given minus 26 Newton meter square per coulomb times epsilon 0, and epsilon 0 we know is a number 8.85 times 10 power minus 12 in SI unit. So charge will be this many coulombs inside, right? You can see it's a negative charge, but he is absolutely correct. You don't know anything else. This could be just 1 point charge. You know, this Q enclosed could be maybe just 1 negative point charge here, or it could be, you know, 2 of them. Maybe there could be a negative charge which is Q enclosed over 2 here, and there could be another one Q enclosed over 2 here, because is the net charge still the same? Yeah. Or you could have, you know, some crazy distribution like this, you know, of negative charges. You could even have some positive and negative charges inside such that the net charge turns out to be this. There's nothing else that is told said to you except for the net flux, right? And net flux only tells you how much is the total charge enclosed, right? The only time you can easily find the electric field inside or outside is when the, say for example, all the charge inside was say a point charge. But then also he's absolutely correct. If the charge was, say for example, if the whole thing was a point charge over here at the center, then you could say that at point P the electric field is radially inward because negative, right? And it is going to be this way, and you can even find its magnitude. But this is not given to you. You don't know that this is the situation. This information doesn't say that the charge is at the center. Is everybody appreciating why they are correct? Because this thing doesn't say where the charge is located. It just says what the flux is. All right, let's look at the next question. Okay, it says the diagrams below give the pattern of electric field lines near each of the 3 insulating balls that may or may not be charged. Sadly, we couldn't measure the electric field inside the ball, so you only see the pattern outside. The full pattern is three-dimensional, of course, but these cross-sectional drawings are qualitatively correct. And what that means is that in this case you see 6 electric field lines going out. In this case you see 4 electric field lines going out, 4 going in. In this case you see all 8 electric field lines going in. Okay, so that is qualitatively correct, you know, 6 going out versus 8 going in. Remember I told you that you can actually choose, if you draw say for example 4 going in one case and 8 going in the other case, that would mean that somehow what, there must be twice as much charge in the other case, right? But the thing is, it's up to you to decide whether you want to draw 12 and 24 or whether you want to draw 4 and 8, but doubling of the lines would mean twice as much charge. So now in this case you can see that this is the field lines. Now here are the statements that you have to choose from. Balls A and B definitely carry a net positive charge. Balls B and C carry a net charge of the greatest magnitude, so both of these carry the same net charge, and these are greatest, that means these are greater as opposed compared to this. Ball C contains a single point charge. Choose all of the statements that are true. Here are your choices. Talk to a person next to you. You have 1 minute. All right, is statement 1 correct? Balls A and B definitely carry a net positive charge. Can we say that about ball A, that it carries net positive charge? Yes, because the electric field lines are going out, right? What about ball B? How much is the net charge there? 0, because you can see as many field lines are going in as are coming out, right? So the net charge inside ball B is definitely 0, because based upon the flux is how many going in versus going out, the net of that, you can see there is no net flux through B, and if there's no net flux through B, because as many field lines are going in as coming out, there cannot be any net charge inside, right? So that is a false statement then, if it says that they both carry net positive charge. That's not true. What about statement B? Balls B and C carry a net charge of greatest magnitude. Obviously if B has no net charge, it is not greater than say for example A, so that cannot be true. Ball C contains a single point charge. Again, just based upon the same kind of logic, by looking at your field lines you cannot say anything about how the charges are distributed, right? It's possible, for example, that you have just a point charge here, negative point charge, so that field lines are going in. It's possible that you have negative charges distributed in some kind of a spherical shape or something. All of those will create electric field that is, that might be pointing inward. Does that make sense? So looking at the flux, it's not possible to say exactly where the charge is located and whether it's a point charge or not. So the correct answer here is none of the above, which most of you got. That's great. Any questions, folks? Okay, so here is the next question. It says the figure below shows a hollow conducting metal sphere which was given initially an evenly distributed positive charge on its surface. Then a positive charge plus Q is brought up near the sphere. What is the direction of the electric field at the center of the sphere after the positive charge Q is brought up near the sphere? Those are the choices. Please talk to a person next to you. You have 1 minute to answer.
Right. That would be absolute. And then after the charge is brought up,
Okay, folks, I want you to understand that this is a conductor, right? Okay, go ahead. 7 seconds. 5 seconds. Okay, the correct answer here is zero field, because remember, the electric field inside of a conductor is zero. In fact, so long as there is no charge inside the cavity, only charge in the cavity will produce an electric field. Remember, the inside of a conductor is shielded from any charge outside. In fact, you know, no matter how much charge you had put here, and no matter how this charge was distributed here, it wouldn't matter. The electric field, even if I had asked you here, what is the electric field due to it? If it's a hollow cavity, wouldn't the electric field be zero everywhere inside the conductor? Does that make sense? And even if it was not a cavity, even if it was a short put, even then, remember, all the excess charges you put on the conductor go on the outer surface. It's a sphere, right? They'll uniformly distribute. Electric field due to that inside will be zero, and this charge, for example, will induce some negative charges here, some positive charges here, such that the net electric field due to all of these charges together should be zero at every point inside the conductor. So suppose in the exam I changed this question slightly and I didn't ask you what is the electric field at the center. I asked you what is it, say for example, over here inside the conductor. What would the answer be? Zero. Because the electric field inside the conductor is always zero in equilibrium. And this rearrangement of charges happens extremely fast so that the electric field becomes zero. All right, let's look at one more before we move on. It says the figure below shows an electric charge Q located at the center of a hollow uncharged conducting metal sphere. So here is a charge Q, and then outside is a charge plus capital Q. Both charges are positive. Choose the description below that describes the net electric forces on each charge in this situation. Both charges experience the same net force directed away from each other. No net force is experienced by either charge. There is no force on capital Q, but net force on small q. There is no force on small q, but force on capital Q. Both charges experience a net force, but they are different from each other. So basically you have to think about, will the little q charge know that there is a capital Q? So will it know its influence? Will it know that there is another charge present? And will the capital Q charge know that there is a small q charge? Because if they know about each other's presence, then they know that there is, you know, then there will be a force on them, right? All right, talk to a person next to you.
Well, I mean, it's metal, so.
Okay, this question definitely requires some thinking. So please think carefully about this question.
I think it's.
no, but I mean negatives of the same charge will go inside on this side. Inside one of the sections. There's definitely no force on Q. There's no force on Q, but there's force on the big Q.
10 seconds. Oh boy, you guys did really well. So the correct answer here is D. Can anybody explain why that is the correct answer? Because this is actually a question that does require some thinking. What is, tell me why you chose D if you chose D. Anybody wants to share their thoughts? Why is the force zero on the charge in the, inside the conductor? Go ahead. Yeah, if it's inside, remember the force on any charge is Q times the electric field, right? So if the electric field is zero, the force is zero. That's for sure. Isn't that true? An electric field everywhere inside this conductor, because it's conductor. Everywhere inside the conductor the electric field is 0. So inside conductor electric field is 0, and that means the force on any charge, no matter how it looks, will be 0 too. On the other hand, what about the charge outside? Why does it feel a force? Can anybody draw a diagram, for example, of this situation with induced charges to show that there will be a force? Can you? Yeah, you could. For example, what would happen in this situation? So here is a conductor, here is a cavity. In the cavity you have put this charge plus Q, right? What will it do? First of all, I think let me just to show exactly what will happen, let me just give some width to the conductor. So this is my conductor. Okay, what will this charge? I'm a scientist working in this cavity of this conductor. This is my room, spherical. What will this plus Q do to the walls of the conductor? Tell me. What would be the non-equilibrium situation? Non-equilibrium situation will be that this is the only charge, right? And then the electric field lines due to this are radially outward and they are penetrating all through the conductor. When they start penetrating this conductor here, will the free electrons in the conductor start feeling a force? Yes, and free electrons will feel a force since they are negatively charged. The force that they feel is opposite to the direction of electric field, wouldn't it? And so which way will they accelerate? If the electric field due to this positive charge is going this way, the electrons over here will feel a force that way, wouldn't they? Similarly, if the electric field due to this charge is this way here in this conductor, the electrons will feel a force in the opposite direction. So then, do you see that the electrons are feeling a force inward in this conductor like this? And so there will be negative charges induced here. And where are those negative charges coming from? They are coming from the outer surface. So the outer surface now has positive charges left behind which don't have electrons next to them, so that you see some positive. And so you can see that this positive should be exactly equal to this negative here, right? Because it's basically these electrons, free electrons, that left and came to the inner surface. Now, if this is a conductor and these charges are uniformly distributed here on the outer surface, by the way, if the charges are uniformly distributed on any sphere, what would be the electric field due to those charges? Remember, we already did using Gauss's law. So if you are given a situation like this, you are told charges are uniformly distributed on anything. It doesn't matter whether it's a conductor or an insulator, but there's uniform charge on the surface, okay? And you are asked, what is the electric field, say, anywhere inside? What would you say? Huh? Anybody? It doesn't matter whether it's a conductor or an insulator. If the charge is uniformly distributed on the surface of that thing, we already used Gauss's law to show that the electric field everywhere inside that thing will definitely be 0. Will definitely be 0, right? So the thing is, so the charges on this outer surface obviously are not producing any electric field in the conductor here. But then the point is that these induced charges on the inner surface will produce an electric field here. And do you remember that? So what I'm trying to say is that this is definitely 0 due to outer charges, right? But if I had asked you this question, what is the electric field here, which is, say, at a distance r away, due to this charge, which is, say, Q, uniformly distributed, what would you have said? Yeah, it's just as though all of the charge which was uniformly distributed on the surface of the sphere was actually a point charge at the center. Do you remember we had seen that? So that means the electric field here has a magnitude which is k q over r square, which is pointing out, and it's just as though this whole thing was replaced with just a point charge at a distance r away, right, from the point where we are trying to find the electric field. So then can you see that this charge anyway produces 0 electric field? The outside charge on the outer surface, this plus q, produces how much electric field? Suppose if I'm looking at the contribution of each of these charges and thinking which one cancels which one, right? Is everybody convinced that this charge on the outer surface of this conductor is definitely not producing any electric field anywhere inside, because that charge is uniformly distributed on the outside, and due to that the electric field everywhere inside is 0. The other thing that you should see is that this charge inside, this minus q here, you know, if this is a sphere and this charge is at the center, this minus q is uniformly distributed here. You know, this point where I'm trying to find the electric field is outside of this, and so can I think of this minus q charge as being at the center for the purposes of calculating electric field? So then due to this minus q, the electric field will be just kq over r square, but it will be radially in. Hey, there's another charge plus q which is at the center anyway. Do you see that it's as though these two cancel each other's effect out? So the net electric field is 0, which is what it should be. Is everybody understanding? I'm just trying to break things down into different parts, and I'm just saying the outside charge does not produce any electric field anywhere inside this conductor, because we have to prove that this will be the induced charge. This is the right induced charge if we wanted the electric field to be 0 everywhere inside this conductor, because that's what should happen in equilibrium. And I'm saying you can show it, you can reason about it, because you can say, hey, all these outside charges uniformly distributed produce 0 electric field anywhere inside, so I don't have to worry about them. This inside charge, this charge, you know, happens to be inside in some sense for this point, any point here on the conductor, right? And so this charge will produce an electric field here, but it will be as though this charge, which is minus q, was located at the center. Now this charge plus q is producing an electric field here also, and that electric field cancels the electric field due to this negative charge, so that the net electric field is 0. Is everybody clear on this? Now here is the thing, if I asked you, if in the exam you got a question like this and you were asked, for example, draw the electric field lines here, how would you draw the electric field lines here? So I want everybody to talk to a person next to them and now say this is a question on your exam that says here is the situation, okay, you can see the charges plus q at the center, minus q here, plus q on the outer surface. Please draw the electric field in the region outside, in the region over here, and in the conductor. Everybody should be talking to a person next to them, because that will make the answer to this question clear immediately.
No, oh, okay. Right.
All right, anybody from the second row, tell me what would the electric field lines look like over here? Second row, please. Anybody? Go ahead, folks. You know, this is not a test right now. This is just learning opportunity. And you should anyway learn to say things. I'm telling you, it's not a test. It's going to only make you a leader. You know, so don't worry about making a mistake. That's the way people learn. We all learn that way. Anybody? Go ahead, please.
Wouldn't they be like radially outward?
Excellent. So the thing is, over here, the electric field will be radially outward, and which charges are producing that electric field? The only thing that is producing an electric field in this region that is radially outward is the positive charge on the outer surface, because we already said, that this situation we said, you know, a few minutes ago, what we were discussing is that this situation can be mapped onto a problem which looks like this. I'm just saying that it's equivalent. So it's equivalent to having a plus q and minus q on top of each other, and then having a plus q on the outer surface. So this arrow here says equivalent. Why? So equivalent for a point outside. For a point outside the sphere, remember we said that you can think of this charge, right? Can you think of that charge as being, since it's uniformly distributed, to be at the center? Because outside we said it produces the exact same electric field kq over r square as though it was a point charge, because point charge produces an electric field also which is kq over r square. So for a point outside, uniform distribution of charge acts as a point charge. So this is exactly like this for a point outside the sphere, right? You can see that that means plus and minus, these two things pretty much cancel out for a point outside. So then the only thing that must be producing an electric field for a point outside, anywhere outside in this region, you know, starting from this r to say this r to this r, any r is a variable, little r is a variable. And I'm just saying for all of these points, the only charge that is producing an electric field is this positive charge, right? And that too, we know that positive charge for a point outside, say here or here or here, produces an electric field as though all of this positive charge was also at the center. Isn't that true? So that means for these points, the electric field will be radially outward, and that's exactly what he said. Is everybody seeing that? Now what about for, sorry, this plus q was supposed to denote all of this plus q collapsed over here because of this equivalence of charge uniformly distributed on the sphere with a point charge for a point outside, right? Now if I start thinking about, say, a point here in the conductor, what is the electric field there?
0.
Yeah, it's 0. We just discussed, right? And it's 0 because if I choose a point here or here, what is the electric field produced by this charge? Will it be 0? Because aren't these points inside for this charge? And remember, we just proved using Gauss's law that if charge is uniformly distributed on a surface, it produces 0 electric field everywhere inside. Is that making sense? So the electric field everywhere here is 0. Okay, who wants to tell me now? Now this equivalence does not work if we are looking for electric field here in this region. Who wants to tell me what would be the electric field in this region here? Please.
It'd be radially outward from the point charge in the middle to the inside of the conductor.
So you are saying like this? Okay, very nice, excellent, this is correct. So the thing, and which charge is producing this electric field? It's only this point charge, right? Do you see that this negative charge happens to be, if I'm asking you what is the electric field here, and this is my r, or if I'm asking you what is the electric field here, and this is my r, if I choose my Gaussian sphere here through this point or through this point, do you see that this charge is outside and this charge is outside and all of them are uniformly distributed? They produce no electric field here, 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 anywhere. The only electric field is due to the charge in the cavity. And that's exactly what we have been saying all this time anyway, that all of the charges inside the cavity are the only ones that are going to affect my experiment if I'm working in a cavity, right? So basically the point is that here this charge produces no electric field here, and there's electric field only produced here by the charge, this positive charge here, right? And it produces an electric field that is radially out. Any questions about this? If this charge was a little bit shifted, then what do you think would have happened? So the question is, if suppose here is my conductor, if the charge was shifted, so the scientist is doing an experiment a little bit shifted from the center of the cavity. In this case, you might have more negative charges induced here than on this side. But again, and because of that, you know, there'll be positive charges induced here. But it turns out that the positive charge on the outside will still be uniformly distributed and will produce zero electric field here in the conductor, and these negative charges and this positive charge will produce an electric field that cancel each other out, so that the electric field inside the conductor everywhere still stays zero. Because isn't that what equilibrium will be? That the electric field everywhere inside the conductor is zero. There is no force on free electrons. Because remember, otherwise F is equal to QE. If there is an electric field inside the conductor, there will be a force on free electron. They'll start to move around. Then it's not equilibrium. And it turns out charges move around extremely fast and equilibrium is established very fast. So does that make sense that there is no force on Q because the electric field here, why is there no force on Q? Because if suppose now I put a charge here, another charge. If I put that charge here, do you see this plus Q will induce some minuses here and it will induce some pluses here, won't it? Some extra things. You can always use superposition principle, remember. So if you do that, is everybody seeing that this charge will induce this minus and plus in such a way that the electric field here stays zero? Because this is a conductor. And so that means if this charge is electric field is not producing any electric field here, F will be zero on this, right? But is the influence of this charge going to be felt here? Yes. Why? Because look, this is inducing these charges here. We just said, you guys yourself said that this charge here is eventually leading to these electric field lines. Do you see that? So do you see that if I put a charge plus Q here, this is feeling a force this way because F is equal to Q times E. So the influence of this charge is to induce these charges in such a way that the electric field outside is not zero, and so this charge will feel a force. In fact, you will do an exploration assignment in the next 2 weeks in which you will see that the word shielding means that the inside of the conductor is shielded from any charges here outside. But it doesn't mean that whatever charges are inside will not affect something outside. It doesn't mean that. So outside is not shielded from inside. It's inside that is shielded from outside. Does that make sense? Okay. Let me actually show you something here. This experiment here is showing you that the electric field inside this conductor is zero. You can see right now what I have here is a conductor. This thing is a conductor. It's very much like this cup here. I have it inside. At the end of the experiment you can come and check it out. But this is really a conductor here, and if that's a conductor, the electric field inside the conductor will be zero, and so even though I have put charges here on this conductor, there's another conductor here, this one, look, these charges are not producing any electric field inside this conductor here, right? The only electric field is in this region between the two conductors. Right? Is that making sense? So basically, I mean, actually the situation that I have here is somewhat like this. Let me draw it for you. This situation is like this. You have a conductor. This is a conductor. And let's say that this is an insulator here. It doesn't matter. So it will make things clearer. So suppose you have some insulator here. And the insulator has some uniform charge. Let's call it Q. All right, this is a conductor here. There's no charge here in the cavity. Can you tell me what would happen in this situation? And there is also some other charge, let's call it plus capital Q over here. So I want all of you, because that's the situation given here, I want all of you to think about what will happen if I put some charge plus Q at one location on this conductor there's a charge plus q here on the outside, what would be the net charges everywhere? Can you do this? Take a minute to talk to the person next to you. Think about what would be the effect of this and what will it eventually, what will happen eventually.
I think the positive electrode is positive on the outside, so it won't be as far away. So it's negative
All right, somebody from the third row. Somebody from the third row. Again, you know what is a really good way to do things? Think of them slowly, one by one. You don't have to think of all the 5 charges together because that's how you get confused. You can always use superposition principle. So don't worry about dealing with 500 charges at the same time. Deal with one at a time. If this charge is on an insulator, is it stuck there? Yeah, that's just stuck there. Because charges on the insulator will stay the way they are. What happens to this charge? Will it stay there? This is a conductor. Will charges move around? And if it's a spherical conductor, what will happen to those charges? Anybody? Third row? Go ahead, folks. Go ahead, please.
It'll be uniform distribution.
Yeah, because it's a spherical conductor, these charges will uniform distribute themselves on the what surface? Outer surface. All of the excess charges always go to the outer surface. Remember we had proved it last time using Gauss's law? The only thing that will induce a charge on the inner surface of the conductor will be if there is a charge in the cavity itself. If I'm a scientist working inside the cavity, those charges will be the only ones that will induce some kind of charge on the inside wall of the cavity, nothing else. All the excess charges you dump on the conductor, it'll immediately go to the outer surface. What would have happened if I had initially patched it over here plus q? Would it still have run out? Yes, in fact I'm going to show you in a minute that is exactly the case. So all of the excess charges always goes outside. So if this is the situation, so this thing is plus q uniformly distributed on the outer surface. So this is it. If this is uniformly distributed and this is uniformly distributed, what is the electric field here? 0. So E equal to 0 in the conductor. Remember, because charges uniformly distributed on the sphere produce 0 electric field everywhere inside. Okay, so electric field is 0 everywhere, and that's what you see here. You see that there's no electric field in this region, right? That's why these nylon fibers, they are not orienting themselves in any particular direction. If there was an electric field, they would try to orient themselves in the direction of the electric field. Now what about the electric field over here? Is there an electric field? Which charge is producing it? If this is uniform distribution of charge, is that producing an electric field here? No, because these points are inside. If you think of this distance r here, this point is actually inside this thing. So there is no electric field at this point due to this plus small q. The only electric field is due to this capital Q, and it is as though this capital Q was at the center. So the electric field here, if suppose this distance was r, will have a magnitude E is equal to K capital Q over r square. Does that make sense? Why? So there is an electric field here, and since it's positive charge, does everybody see that the electric field lines will be going out like this? Everybody clear? Okay, now tell me what about over here? What would be the electric field at a distance r away? Let's give it another name, let's call it r1. r1 away, r1 is the distance from the center to this point. I want to know what is the magnitude and direction of electric field. Direction you already know, it will all be radially out, right? Again, won't it be radially out? But which charges are producing electric field outside? Tell me, folks. Somebody from the last row, which charges are producing an electric field in this region, please?
The little q
Excellent. It is the little q and the big Q, and it is as though both little q and big Q are situated at the center. Remember, for a point outside, if you want to find the electric field, you can think of the charge uniformly distributed on the sphere as though it was located at the center. So this is going to be K times Q plus Q divided by R1 square, where R1 is this distance. Is everybody seeing that? Folks, what would have happened if suppose this was not positive, but suppose this was negative and exactly equal in magnitude to this plus Q? So the question is this. Now the question is, and in fact this is a situation that we will encounter a lot later on. So the question that I'm asking you is, okay, this is my conductor. I'm shading my conductor. All I'm trying to say is, who wants to tell me what would happen if I have, say for example, plus Q on this conductor, which we said will uniformly distribute, right? And suppose this was minus Q, minus capital Q, uniformly distributed. What would be the electric field here at a distance R1 away? What did you say? 0. Does everybody see that this is 0? Why? So the electric field everywhere outside here is 0. And you know, oftentimes the wires that you use in your houses, you know, these coaxial cables, they have two metal cylinders, metal wires, one wrapped over the other, and there's an insulator in the middle. And it turns out oftentimes what they do is they put positive charges on one of them and equal amount of negative charge on the other one. And what is the advantage of doing that? That the electric field is restricted only in the region between those conductors. There's no electric field outside. In your room, there won't be any electric field due to these coaxial cables if they have positive charge on, say, the inner cable and negative on the outer, or vice versa. But if they are equal in magnitude and opposite in sign. Do you see why this will be 0? Because we can use the same exact logic here, same exact logic, and what we see is that this is K minus Q plus Q divided by R square, which is equal to 0. So what we see is that this negative charge minus Q can be thought of as a point charge here. This positive charge can be thought of as a point charge there. It's as though there was no net charge because of both these at a point outside, right? In fact, later we are going to talk about these things, coaxial cables. We are going to talk about spherical capacitors, and spherical capacitors will have equal and opposite charges on two metal plates. And you will see that the electric field will be non-zero only in this region, and it will point from positive to negative. So do you see that the electric field is not 0 only here? Electric field is 0 here still. Exact same argument as here, right? Electric field is 0 outside also because Q and minus Q cancel out, cancel each other's effect. Any questions about this, folks? Okay, so is the answer clear here? Why is it that inside charge feels no force? Because the electric field is 0. Outside charge, it will feel the force due to the induced charges on the surface. Okay, let's move on. Oh, I wanted to show you this demo here. So this thing, by the way, this device is called electrophorus, and you have already used it, right, in your exploration center. So basically what I'm going to do is do something similar to what you had done. So let me rub this. If I rub this with fur, what do you think will happen? Depending upon which one has more affinity for electrons, one thing will become positively charged and one thing will become negatively charged, right? Okay, in physics we don't really care about which one is positive and which one is, we don't care to memorize things. So let's say that this one is positive. Okay, so if this thing becomes positive, if I put this metal on top of it, do you see that if this plastic surface is positive, negative induced charges will be induced closer to the surface and positive on the outer surface? Wouldn't it be that way? So what I'm trying to say, oops, is this. In your exploration assignment, for example, here was your, suppose you have positive charges. This is my plastic thing, and this is my metal plate. Now metal plate has two surfaces, right? When I bring it close, do you see that negative charges will be induced here and positive over here? Because positive and negative like each other, right? Now what happens if I ground this? Anybody wants to tell me what happens if I ground it? Please.
The negative charges will come from the ground.
Excellent. The negative charges will come from the ground, neutralize these positive charges, because these positive charges really hate being close to, you know, these positives anyway, right? So they will basically get neutralized by the negative charges, so you won't have any charges on the upper surface. Now if you remove the grounding first, you have trapped negative charges inside this metal, right? If you carefully lift this metal with an insulating handle, make sure that you have to have an insulating handle, because my body is a conductor too, otherwise if I touch it, I'm going to pick up charges from there, right? So the thing is, basically you pick it up, this thing has negative charges, right? It's true that those negative charges will distribute themselves once you lift it. Once I have lifted this thing like this, this is this thing here, the negative charges will distribute themselves in such a way such that what happens to the electric field everywhere inside the conductor? It becomes 0, right? So if that's the case, let's try and see what happens. So I'm putting it here, I ground it, this is my grounding wire, it's connected to earth. Now I lift it. If I now touch it to this ball, this metal ball, will I give some of the charges to the metal ball? And look, this is a electroscope. Uh-oh, the charge is not very much, so let me rub it harder. Okay, here. All right, let me lift it. Here is the thing. You can see that there is charge here, right? In fact, the electroscope was showing something, you can see, right? Let me try to neutralize it. See, do you see some charges here? The electroscope is showing some deflection. Okay, now what do you think will happen if I put it inside here? Actually, I think the charges jumped. Sometimes what happens is that there can be something similar to lightning. Remember we said that lightning means that the electric field exceeds the breakdown voltage, and you actually the air starts behaving like a conductor. When you have the static, when you feel static, when you touch something, similar kind of thing is happening. Air is becoming ionized and charges are jumping from, say for example, doorknob to your body. Do you know what I'm saying? Or from your body to doorknob. If you walk on the rug a lot, your body picks up charge just by this rubbing, and your body has a lot of charge. Now you touch the doorknob, you see the spark. That means the air between your hand and the doorknob has gotten ionized, because the electric field due to the charges on your hand, for example, may have exceeded that breakdown voltage of 3 × 10⁶ newtons per coulomb. So let's try to do it one more time here. Okay, so now I'll lift it. This thing has charge. Now I'm going to touch it with this. I'm going to give some charges to that thing. Let's now try to see. Look at that electroscope there. Somehow this turns out to be very difficult. Okay, you do see some deflection, right? So why is it that there is deflection? Do you think there's any charge left in the inside? Actually there isn't, because you know what has happened? We have basically done this. What we have done is we have brought, think of this metal, and what we did was we touched here, you know, with some charge here. We said, okay, let's put plus some charge, plus Q1 over here. The problem is all that charge will immediately move to the outer surface of the conductor. Remember, it won't stay inside. So all of the charges from this, as soon as I touch this metal ball, all that excess charge has gone outside now. So there's no charge left, and I can show you by, look, I mean the thing is there's no charge left here. You know, this is a very sensitive electroscope. You can see hardly any deflection can be well, somehow it's not coming very well on this thing. The point is there is no charge left on this, because all the charges have gone on the outer surface. Does that make sense, folks? Any questions about this? Anybody? All right, then let's move on. And before I get to electrical potential, which is our next chapter, I wanted to ask you one more question that you should think with the person next to you, and that would be, again related to electric field. Here is the thing. If you have a positive charge on one surface of a sheet of charge, infinite sheet of charge, another sheet of charge has negative charge. Remember we said that this configuration is called a parallel plate capacitor? Do you remember that? So the electric field between the two plates points which way? Right, it always points from the positive charge towards the negative charge, and in this case this field is pretty uniform. This electric field is pretty uniform. Now the question I have for you is, if I take the metal ball, this metal ball, and I bring this ball and put it in this electric field here, like this, what do you think, how do you think it's going to change the electric field lines? What will happen? Please talk to a person next to you for 1 minute and then we'll discuss this. So the question is
it neutral?
yeah, the ball is neutral. So bring a neutral ball.
How would it affect the yeah, but it wouldn't change the field itself. It would just adapt to the field.
All right, anybody has a thought? How about somebody from the fourth row? Anybody wants to share their thought? What might happen in this case? Will putting a metal ball somehow induce charges on the surface of the metal ball? Because it's now in an electric field, right? So what do you think will happen? Look, these electric field lines, so this is the non-equilibrium situation right now, right? So the non-equilibrium situation is the situation in which these electric field lines are penetrating through the conductor. What will these electric field lines do to the free electrons in this thing, in this metal? Will they produce a force on it? Yes, and in fact we know that F will be equal to QE, and because of this the free electrons in this metal will feel a force which way? Opposite to the direction of electric field. And in fact we know that negative charges, these free electrons will come and pile up on this surface, and they'll leave behind positive charges on the other surface in such a way that the electric, when will this movement of charges stop? When the, how would you know that this is the, this will be the situation when the movement of charges has stopped, will stop. When? What has happened? Sorry, what I meant was, how will you know that this is the right situation for the movement of, for the acceleration of these charges to stop? When what has happened? Did you want to say something? How would I know that this is the right situation for the movement of charges to stop, the acceleration of charges? Go ahead.
The electric field would be 0.
Yeah, you always have to remember this. In a conductor, movement of charges will, the acceleration will keep going on till the electrons feel no net force, and that means the electric field has become 0, because no net force when field is 0. And so E should become 0 everywhere inside. And you know what you will notice? That these charges actually even distort the electric field outside this conductor, and outside this conductor the electric field lines will always land. Remember, electric field lines always start at positive charges, they end at negative charges. So in this case what you will notice is that the electric field lines always land perpendicular to the surface of the conductor. What do I mean by that? If you draw a tangent here to the surface, the angle at which the electric field lines land, this angle is 90 degrees. Similarly, if you draw a tangent here to the surface, you will see that the electric field is landing at a 90-degree angle. Similarly on this side, the electric field lines will go out from the positive charge and they will go out in such a way that at any point, if you draw a tangent, there is a 90-degree angle between the electric field and the surface of the conductor. Why is that the case? Why should the electric field lines always land at 90-degree angle? Because see, if they didn't land at 90-degree angle, suppose this angle here, suppose this line was like this. At this case, you know, if I draw a tangent, maybe this angle is 30 degrees or something. In this case, what will happen is that this electric field actually has a component parallel to the surface. What will that parallel component do? Will it exert a force on these positive charges that are on the surface? Yes. And because of that, you know, the electrons here that are there will start moving in the opposite direction. And that cannot be the case. So this situation is not right. The correct situation would be when the electric field lines always land perpendicular to the surface here, so that there is no component of electric field parallel to the surface. So that means the free electrons on the surface do not feel any net force and don't start accelerating, because if they do, then it's not an equilibrium situation yet. Does that make sense, folks? Anybody has any questions about chapter 3:23? Anything? All right, then now we are going to move on to a completely new formulation of the same exact thing. This shouldn't be a new thing for you, because you have seen this even in mechanics course. For example, we are going to introduce this new concept called electrical potential energy and electrical potential. Now you might say, and what you will see is that this new way of thinking about things is not going to get us some new results really. Anything that we knew how to do using force and field, we will now try to see if it's easier to do using potential energy and potential concepts. So it's just a new way of thinking about things. Do you remember in mechanics, for example, again, you could talk about forces, which is what you did when you were doing Newton's laws of motion, right? You were talking about free body diagram, what would be the net force on some object whose free body diagram you were drawing, and you could do a lot of things. So I could have asked you, suppose you throw something from a cliff, I throw a ball from a cliff, what would be the speed of the ball when it goes to the ground or something? In this case, again, I could say, okay, the only force on this ball is, say, gravitational force, or if you take into account the air resistance force also, take it into account, that's fine. But knowing the net force, you could find its acceleration, and then you could actually use equations of kinematics to do this problem, right? On the other hand, what method did you find much easier if there was no air resistance force? Is it much easier to use the energy concept and to say, oh, if there's no air resistance force and if there's no work done by non-conservative forces such as friction, air resistance, etc., the mechanical energy of the system, which is the sum of what? What is mechanical energy? Anybody? Sum of potential energy plus kinetic energy. It should be constant, and that means the potential energy plus kinetic energy here should be equal to potential energy plus kinetic energy there. So if it goes down, you lose gravitational potential energy, you must gain kinetic energy, you can figure out what is the speed at the bottom. What was the advantage of doing that? Because you need to see, we'll exactly do the same thing here, except we are not going to talk about gravitational potential energy, we are going to talk about electrical potential energy. Because it turns out that Coulomb force, just like gravitational force, is also a conservative force. And that means if you just have Coulomb force, if you just have electrostatic forces between this charge and this charge, there's no work done by non-conservative forces, so mechanical energy of the system is conserved. You can again say, oh, mechanical energy here is equal to mechanical energy here, but this time when you try equating potential energy and kinetic energy, you are going to use the potential energy to be the potential energy due to the electrostatic force. All right, I mean in general you should include all types of potential energies, so even gravitational thing, but if suppose gravitational effects are very small, suppose charges are moving horizontally, obviously there's no change in gravitational potential energy, right? So in those cases you just have to worry about electrical potential energy. So let me just remind you why this concept is useful, because the thing is the ideas are going to be exactly identical to what you have already learned. We are not talking about anything fancy, anything novel. The same exact thing applied to a new situation. But I do want you to appreciate the virtue of using energy and energy concepts. So tell me, what is one big advantage you see of using energy concepts in your mechanics course compared to force concept in your mechanics course? Tell me. You know, because in your mechanics course, if I told you, the question I have for you is, why is it that energy is so much easier to use than force if you can use energy concepts in the same problem? Because problems can be done in more than one way, right? So if I have a cliff here, and suppose I told you a ball was thrown with a speed of say 30 meters per second at an angle of say 20 degrees from the horizontal, this height h is equal to 100 meters. Tell me, what is the final speed of this ball when it hits the ground, right? Another question I could ask you, and I told you, please ignore the air resistance force. Another question I said is, this time I'm throwing it at 20 degrees below horizontal. V is equal to, again, 30 meters per second. It's the same exact cliff. And again, I'm asking you, can you tell me what will be its speed when it hits the ground? First of all, could you use force, kinematics and dynamics as opposed to energy to do this problem? Or not? You could. Nobody will stop you from saying, oh, I want to think of this ball as a projectile, right? I'm going to look at its x component of motion, y component of motion. I will find the Vx and Vy. And then I'll say, oh, the speed is equal to square root of Vx square plus Vy square. These are the x and y components of velocity. You could do that. You could do that here. You could do that here. Is that what you will do if you got this thing on the test? What would you do? Go ahead, please.
Use conservation of energy.
You would use conservation of energy. I mean, at least 95% of you will say, no, I'm not going to treat it as a projectile, although I know that will work. There's nothing wrong in treating these things as projectile, but I will use conservation of energy. You know, one advantage of using conservation of energy is, are these two problems separate or are they the same? Is the answer to both of them the same or different? Huh? Why is it the same? Because is the initial, if this thing is sent from, if this thing is thrown at an angle of 20 degrees above horizontal at this speed, and this one's thrown below, and you are asked for the speed, do you see that the speed here, that means kinetic energy at this point doesn't care about the angle. Kinetic energy is a scalar quantity. So half mv square on the top over there is the same, right? And mgh, which is the gravitational potential energy, is the same here and here, right? So you can see that the final, and if the final gravitational potential energy is the same, the kinetic energy should be the same, which means the speed should be the same for both, right? So in fact, these two problems are not separate if you think of them as a energy problem, because energy is a scalar quantity, it doesn't deal with direction. On the other hand, if you were using projectile motion and forces and thinking about all those things, then you will not be able to convince yourself that when you find the x component and y component and you take this, you do the Pythagorean theorem here and here, it will turn out to be the same thing. It will not be so easy for you to convince yourself, yes, that is the case. The best way to convince yourself of that is to think of the energy conservation, mechanical energy conservation, and say, hey, these two problems are really the same. Mechanical energy conservation says the answer for the speed must be the same in both cases. You don't even have to do it twice, just do it once, write the answer must be the same on this argument, you get full credit for both. On the other hand, based upon force arguments, you'll have to do it twice if you were to do projectile, kinematics and dynamics and those things. Same is the case here when we are dealing with electrostatic forces and fields. Forces and fields here again, you have seen in these three chapters, are vector quantities. You have to be careful in looking at components of things, you know, which way is the electric field pointing, which way is the force pointing, etc. When you deal with electrostatic potential energy, you're dealing with a scalar, no direction. And that makes your life so much easier. So so that is the motivation for introducing this new thing, because you might say, oh, why do we have to learn about a new concept? The reason this concept is important, the concept of potential energy and potential, is yes, we could have done these concepts with forces, but is much harder in some situation to use than the concept of energy, which is a scalar. Does that make sense? That's at least one advantage. We will see some other advantages of using energy concepts and this concept of potential energy later on. So let me first of all again review stuff from physics 1 about what you know about gravitational potential energy. And you know this. What was the work done? Review from mechanics. An analogy with electrostatics. Do you remember this? That the work done by the conservative forces, so for any conservative force, the work done must be equal to, do you remember this? Negative of the change in potential energy. So in other words, this is equal to the negative of the final potential energy minus the initial potential energy. U is the symbol we are going to use for potential energy. So for example, what would be the work done by gravity? Gravitational force? The work done by gravitational force will be again the same, negative of the change in the gravitational potential energy. And close to Earth, this will be mgh final minus mgh initial, because if you remember, the gravitational potential energy at a height h was mgh, right? M is the mass of the object. Now here is the thing. What you have to remember is that potential energy is undefined by a constant value. So, and that is all right. So I can choose my reference height to be anything I feel like, and that is because any physical problem in your life is always going to involve differences in potential energy. It will never involve just potential energy at some point. No physical problem will ever involve that. So it's okay for you to say, I'm going to choose this as my zero of potential energy, and that's where I'm going to measure all the heights, and I'll say, no, I'm going to measure it from there. Our answers for any physical problem will always be the same. Okay? So that same exact thing applies in our case here to the electrostatic case. And we can say that work done by the electrostatic force should be equal to negative of the electrostatic potential energy, which will be equal to U final electrostatic minus U initial electrostatic. Right? By the way, do you remember how we had actually derived this? Is everybody convinced that this is correct? Yeah, because the way we had derived this was like this. We had said last semester this. What we said is that, hey, if you think of a ball, let's say that you had a ball which was initially at some height which we call h of I. This is the initial height of the ball. And then the ball fell under gravitational force and came to some final height h of f. Right? And let's say its displacement was d in the downward direction. The question is, what is the work done by gravity? You know, it's magnitude of force, magnitude of displacement times cosine of the angle between the two, right? that's the work done by a constant force, isn't it? So in this case, what is magnitude of force? What force are we talking about? The gravitational force, and that is the weight, isn't it? mg acting down. Is everybody seeing that? So the force that we are talking about when we talk about gravitational force, so work done by the gravitational force will be equal to mg magnitude times b, and what is d in this case? The displacement is in the downward direction, right? Can I write it in terms of hi minus h of f? Yes. So d is nothing but hi minus h of f and times cosine theta. What is the angle between the gravitational force that's acting down and the displacement which is down to 0? So this is times cosine 0. Cosine 0 is just 1. And so you can see that work done by gravity turns out to be mg h of I minus mg h of f. And this is what we decide to call use of I, and this is what we decide to call use of f, right? And this can be written as negative of use of f minus use of I, which is equal to negative of delta u. Why is it that we are using negative sign? Because always when you talk about changes, you always talk about final minus initial. That's the convention. Okay, and it turns out that work done by gravity is initial potential energy minus final potential energy. So if you wanted to write it as final minus initial, there's a minus sign in the front, right? Exactly in the same fashion. Now instead of gravity, let's think about electrostatic force. Okay, so this time think about this situation. Let's say that we have a parallel plate capacitor with uniform electric field pointing down from positive to negative, right? Electric field between the plates of a capacitor whose plates are extremely large will always be uniform pointing down. Do you see that this is exactly like this gravitational field which is acting down, and it has a constant magnitude 9.8 meters per second square pointing down? Isn't that true? That, you know, here this ball is moving down in gravitational field which is 9.8 meters per second square magnitude pointing down. Here we have electric field that's pointing down. In this case, we are not talking about a mass moving, we are more interested in the charge of that particle. We are not so interested in the mass of the particle this time. So suppose I say, oh, suppose I have now a test charge Q0 and I release it from one of those plates there, right? And suppose I ask you, okay, I suppose I say to you, let's say that from this bottom plate, this height is h of I. And suppose I say, oh, once the charge has arrived here, so once the charge has arrived here, then let's call this height h of f. Suppose I ask you, how much is the work done by the electrostatic force? What would you say? So work done by electrostatic force, will you say again that it must be force times displacement times cosine of the angle between the two? Since the electrostatic force is constant here, can I use the same exact relation? Isn't that always true for any constant force? If it was not a constant force, then I would have to do an integral f dot ds. But this time the force is constant because the field is constant. I can use the same exact formula we use for gravitation for electrostatics. What is the force here in terms of electric field? Who wants to tell me very quick? Tell me, what is the force that this charge Q0 is feeling due to the electric field E in terms of Q0 and E? Q0 times E, very good. F is equal to QE. So this work will be Q times E times, what is the displacement? Can I again call it HI minus HF? Yes, this is HI minus HF. And what is cosine theta? That's the angle between the force that this charge is feeling, which is downward, right? F is equal to QE. So the force on a positive charge is in the direction of electric field, and displacement is also down. So cosine theta is cosine 0. And so work done by the electrostatic force then is equal to Q E HI minus Q E HF. So if I tell you, can you come up with a name for this quantity QEH? Whenever electric field is constant, what would you give that thing a name? QEH. Can you draw an analogy between this case and this case? If we decided to call mgh the gravitational potential energy at height h, can we call QEH the electrical potential energy at a height h from, say, the negative plate when the electric field is constant from some surface? Right. So the thing is, so we can define you know, U as equal to QEH. This is electrostatics in constant field. This is the electrostatic potential energy in constant field. Notice that this is only true for in constant field. If the field was not constant, I would have to do work done is equal to integral F dot ds. Right now, we got a simple answer. And is everybody seeing? Then we can write this as UI U electrostatic I minus U electrostatic F, which is equal to minus UF electrostatic minus UI electrostatic. Is that making sense, folks? This analogy between the two cases? Okay, now the other thing that I wanted to say is that why did we decide to choose to define something called electric field? We just said it will be a convenient thing to do. Didn't we say that choosing an electric field and defining that concept would be a useful thing as opposed to always talking about force? Same is the idea here when we define something called electrical potential. So now I'm going to actually define something called electrical potential. And folks, I don't know what to do because we are going to use the symbol capital V because that is universally used for potential. Don't confuse it with speed, don't confuse it with volume, and don't confuse it with other things. So potential will be capital V, and that will be defined as potential energy per unit charge. Compare it with E is equal to F per unit charge. So I want you to understand why is this concept of potential important? Because exactly in the same way where we can talk about an electric field, suppose there was a charge on his body here and there was some charge on her body and his body, and we were talking, is it okay to talk about electric field at this point where there's no charge that is due to this charge, that charge, and that charge? Yes, it is okay to talk about a field because when you're talking about field produced by some charges in different locations, that's okay. There doesn't need to be a charge here. The good thing is if I knew the field here, now if you told me, oh, if I bring a charge here, what happens to the, how much is the force on it? You just multiply the charge by the electric field and you have the force, right? That's the good thing. And if you decide to bring another charge, I can easily multiply it by another charge and tell you what the field, what the force will be, both in magnitude and direction as well. So field concept is useful for that sense, in that sense. That's exactly the same idea for electrical potential. But when you talk about potential energy of a system, you talk about, you know, interaction between this charge with this charge, etc. But when you talk about potential that is produced at this point by one charge, you don't have to have a charge there. Because potential is defined as potential energy per unit charge. So it's much more convenient to talk about potential. And then if you ask me what is the potential energy of these two charges together, suppose you say what is the potential produced by that charge at this point, I don't need to have a charge here. But then if you ask me what is the potential energy if I bring a charge here of these two things together, all I have to do is multiply that charge by V and I get potential energy. You see what I'm saying? Just like here, F is equal to QE. So knowing E makes it very easy to find force. Knowing potential makes it very easy to find the potential energy. Is everybody understanding the idea here? Okay. One question for you. What is the unit of potential energy? Somebody from the last row, please. Unit of potential energy? Please. What is it? Joules. Put unit of all kinds of energy, no matter what kind it is, heat energy, light energy, potential energy, kinetic energy, all energies is joules. So the unit, what about unit of work? Joules. Obviously looking at this relation and doing a dimensional analysis, you know unit of work better be the same as unit of this energy and this energy because they are all different terms in the same equation, right? So the unit of work is joules too. What would be the unit of potential? Fifth row, please. What would be the unit of potential? I don't want any fancy name. Please tell me looking at this equation. What should be the unit of this thing, potential? Huh? Joules per? Excellent. The SI unit of potential is joules, the unit of joules divided by the unit of charge, which is coulomb. And joules per coulomb has a shorter name. It's called volts. That's just a short name after the scientist who did a lot of experiments related to this, okay? So the SI unit of V is joules per coulomb, and this is called volts, volt, and it's written as V. Any questions about this, folks? Anybody? Okay, I have a question that I want all of us to work together. In fact, I want you to talk to a person next to you, because if I keep doing all the work, you know, learning wouldn't be the greatest. So let me ask you a question. Think with the person next to you. So the question says, the work done in moving a test charge Q0, which is positive and which is 2 times 10 power 6 coulomb, at a steady speed from point A to point B between the plates of a parallel plate capacitor is 5 times 10 power minus 5 joules. Part A says, find the difference in potential energy of the charge between the 2 points, and then it says, determine the potential difference between the 2 points. So let me write down what the question is. So the question is asking, it's giving you this kind of a situation where you have electric field that is pointing like this, and it's telling you, in the question you have been told that some charge moves from point A to point B. So let's say there was a point A here, there is a point B here, and some charge Q, and Q is given to you to be 2 times 10 power minus 6 coulomb. It moves from A to B at a steady speed, and you are given that the work done by the electrostatic force is 5 times 10 power minus 5 joules. The question is asking, part A of the question is, what is delta U? And part B is, what is delta V? Okay? 1 minute. Everybody should be talking to a person next to you and working this out, because all the answers are pretty much written there. It's very simple to figure it out. Alright, who wants to tell me what's the answer to this one? Somebody from this side? How do I know delta U is equal to? Oh, very good. Negative of electrostatic work done by the electrostatic force, and this is negative 5 times 10 power minus 5 joules. Very good. What about the second question, delta V? Anybody? Go ahead, please. How did you come to that? Because?
Divide the changing U over the charge Q.
Yeah, because you have to understand this, that V is equal to U divided by Q, right? So V final minus V initial will be equal to U final minus U initial divided by Q. And that means that delta V should be equal to delta U divided by Q. And that means this should be equal to minus 5 times 10 power minus 5 joules divided by Q, which is 2 times 10 power minus 6 coulomb. And so this is equal to minus 25 volts. Right? Good. Is everybody clear on this? Any questions about this, folks? All right, then I have one more question, one more idea for you here to think about. Here is the thing. So what do you think is happening? The final potential energy is less or more than the initial potential energy. As this charge is moving from here to here, what is happening to the potential energy? You know, it says U final minus U initial is negative. That means the potential energy here is less than it is over there, right? What about the potential then? The potential is negative too. So somehow the potential that is produced by these charges is, you know, decreasing. It's less here. So if we call this thing here V final and we call this V initial, what we are saying here, looking at this, delta V is negative, less than 0. Negative means less than 0. So that means V final minus V initial is less than 0, and that means V final is less than V initial. And so we learned something really important here. What we learned is that what is producing this potential? It's the plates of the capacitor. You know, plates of the capacitor will be producing electric field if you were talking about things in terms of electric field, and that would cause a force on this charge. But now we have changed the language and we are saying plates of the capacitor is producing a potential at different points between the two plates, and that is now, you know, there is a potential energy that is stored in this charge due to that potential. So this is the potential energy and this is the potential difference between 2 points, for example. Right? So potential takes the same role as electric field does. You have to understand this is very much like this. This is very much like in the sense analogy. I'm not saying that force has anything, has the same unit as potential energy. I'm not saying that. I'm saying that they have similar roles to play in this new formalism. So notice that if you are close to the positive plate of the capacitor, is the potential higher here than here? Isn't it? So you can see we are saying VI is greater than VF. That means the potential is higher closer to the positive plate and potential is lower closer to the negative plate. So that means one important thing that you will always see that is true regardless of whether it's parallel plate capacitor or some other thing is that whenever you are closer to positive charges, the potential will be higher. As you go farther and farther away from them, the potential will decrease. So one important conclusion, which is very important, is potential is higher closer to positive charge as you go farther away from a positive charge. potential decreases. Okay, I also want to teach you how to talk in terms of potential as opposed to field, because you need to get used to this new language. So here is the thing, if I had not asked you to think about this problem in terms of potential, but rather in terms of field, in terms of what you have done in chapters 21, 22 and 23, what would you have said about this charge? Would you have said that a positive charge will always feel a force from in the direction of electric field, and a positive charge always accelerates in the direction of electric field? Wouldn't you say that? Right? This positive charge is feeling a force this way, F is equal to QE in the direction of electric field. But in the language of potential, what would you say? A positive charge always accelerates from what kind of potential to what kind of potential? Tell me. Huh? From higher potential to lower potential. Because potential is not defined by a constant value, so you can always add a constant thing to the potential. But do you notice that when this charge is accelerating this way, this side Vi was more than Vf? That means positive charge is accelerating from higher potential to lower, right? So that's a new language for talking about the same exact thing. So you could say positive charge always accelerates in the direction of electric field if you're talking about things in terms of field, like in chapters 21, 22, 23. In chapter 24 now, we will start saying, well, another way to say this is a positive charge always accelerates from higher potential to lower potential. New language, same physics. Does that make sense? So let me just write this down for you. A positive charge accelerates from higher to lower potential. What about if I asked you about a negative charge? What would you say to me? A negative charge will accelerate from lower potential to higher potential. Just like a negative charge will feel a force opposite to the direction of electric field, right? Does that make sense, folks? Any questions about this? Okay, let's do one problem, and this is based upon conservation of mechanical energy, just like you used to do in physics 1, and then we'll leave for today. So it says, in the figure, point B has an electrical potential that is 25 volts, which is greater than that point A. So VB minus VA is 25 volts. A particle has a mass of 1.8 times 10 power minus 5 kg, and a charge whose magnitude is 3 times 10 power minus 5 coulomb. The effect of gravity and friction are negligible. Part A says, if the particle has a positive charge and it's released from point B, what speed VA does the particle have when it reaches point A? And part B says, if the particle has a negative charge and it's released from rest at A, what speed does it have at point B? So in this example, let's first do part A. So you have parallel plate capacitor. This is the positive plate. There's some point that is being called B here. There's some point that we are calling A here. You are told VB minus VA is equal to 25 volts. You are told that there is some charge Q that is 3 times 10 power minus 5 coulomb. And it's saying, part A says Q is positive and released from B from point B. The question is asking, what is the speed when it reaches point A? Is everybody understanding the question? And you're supposed to ignore the frictional forces and the gravitational force. So then the only force that is acting on this charge, so I have this charge plus Q that starts here and then it starts accelerating here, and this is the final position, right? So this is the initial position, and this is the final position here. Can I use mechanical energy conservation? Yes, because there is no work done by non-conservative forces. The only work that is being done here is by electrostatic force, right? Isn't the electrostatic force the only force that's doing work? So since there is no work done by non-conservative forces, we can say that the final mechanical energy of the system should be equal to the initial mechanical energy. And remember, mechanical energy was kinetic energy plus potential energy, and that should be equal to the initial kinetic energy plus the initial potential energy. Now, do you remember kinetic energy is half mv square, where m is the mass of the object and v is the speed. Now, the particle is released from rest. So what is Vb? 0, right? And we need to find Va. What is its speed here? So if Vb is 0, here what we are talking about is this. Oops. Is there no blackboard that is not used? Oh, here. Good. So basically, we have this K final, and final for us is point A. So I can say Ka plus Ua, these are the final things, is equal to K initial, which is Kb plus Ub. Now Kb is 0 because the initial speed of the particle is 0. So what we have is half mVa square. Folks, you have to be very careful because V here, small v will be speed, capital V will be potential. So half mVa square is equal to Ub minus Ua. But can I write this like this? Va square should be equal to 2 divided by m times Ub minus Ua. But Ub minus Ua, can I write it in terms of Vb and Va? I can, right? How can I? Tell me. Yeah, first of all, I can find Va by taking square root of this. So that will be 2 over m. So this is Q times Vb minus Va. Okay, so what is the mass of the particle? Oh, we have also been told that the mass of this particle is, the mass of this particle is 1.8 times 10 power minus 5 kg. So that will be 1.8 times 10 power minus 5 kg multiplied by Q, which is 3 times 10 power minus 5 coulomb, multiplied by change in potential energy, which is 25 volts, and this answer should be in meters per second because everything I wrote is in SI unit. Isn't that true, folks? If everything is in SI unit, the final answer must be in SI unit too. Now the second part is just saying, suppose if the particle has a negative charge, all right, and I'm going to leave this problem for you. So suppose, so all you have to do is go through the same calculation in the second part. This time they're saying this is negative, this is not the final position, this is the initial position, this is the final position. What will happen if this charge is negative? Which way will it accelerate? Up. Does everybody see that it will go that way, opposite to the, so this is the direction of electric field, this is the direction of the force for the negative charge. So that means the particle will accelerate upwards. Can we again use the same exact relation here? Same exact thing here. This time what is 0 is not Vb. What is 0 is? Va equal to 0 and Vb is equal to what? So you can just like go through exactly the same analysis up to here and then choose your Va and Vb correctly and you will get the answer. Does that make sense, folks? All right, have a great day, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.